Modern ceramic coatings have transformed the automotive protection industry, but behind the deep gloss, water-beating, and scratch resistance lies a highly engineered industrial manufacturing process driven by advanced chemistry, nanoscale engineering, and precision production control. Today, we explore how professional 9H ceramic coatings are manufactured on an industrial scale. From silane chemistry and nano-silica, most industrial ceramic coating systems are built around several major formulation components. The first is silane chemistry. Organofunctional silanes act as reactive coupling agents, capable of bonding to painted automotive surfaces, while simultaneously forming cross-linked structures during curing. These materials are responsible for adhesion, film formation, and long-term coating durability. The second critical component is nanosilica reinforcement. Nanosilica particles are incorporated to improve surface hardness, abrasion resistance, and coating stability. Particle size distribution becomes extremely important because oversized particles can reduce transparency and negatively affect gloss development. To maintain optical clarity and smooth surface appearance, manufacturers use highly controlled nano-dispersion systems. The next major component is the industrial solvent system. Specialized solvent blends are carefully engineered to control viscosity, application smoothness, evaporation behavior, and curing performance. Even small solvent imbalances can affect leveling, flash time, or final film consistency. Additional additives may then be introduced to optimize hydrophobic performance, UV stability, anti-streak behavior, and storage stability. Unlike conventional wax products, ceramic coating systems remain chemically reactive inside the container. As a result, moisture control becomes one of the most important aspects of industrial manufacturing. Many professional manufacturers operate sealed processing areas because atmospheric moisture can prematurely trigger silane hydrolysis reactions during production. The manufacturing process starts with solvent charging. Selected solvents are transferred into stainless steel mixing vessels equipped with controlled agitation systems. Temperature control is critical because excessive heat can destabilize sensitive, reactive materials. Once the solvent base is stabilized, silane components are gradually introduced under controlled mixing conditions. Some facilities also use nitrogen blanketing systems to minimize atmospheric moisture exposure during processing. The next stage involves nanosilica incorporation. Nanoparticles naturally tend to agglomerate, meaning they cluster together if dispersion energy is insufficient. To achieve proper particle distribution and optical clarity, manufacturers may use high shear mixers, bead mills, ultrasonic dispersion systems, or vacuum homogenization equipment. Proper nano dispersion directly affects hardness, consistency, transparency, gloss performance, and long-term stability. After dispersion, formulation modifiers and performance additives are introduced. These materials may improve water repellency, leveling behavior, UV resistance, or curing control. The coating then moves into a fine filtration stage. Because ceramic coatings form extremely thin protective films, even microscopic contamination can negatively affect the final surface appearance. Industrial filtration systems remove unwanted particles before packaging operations begin. The finished coating is then transferred into moisture-resistant packaging systems. Many manufacturers use amber glass bottles or specialized barrier packaging to minimize UV exposure and atmospheric moisture penetration during storage. Filling operations are often conducted under controlled humidity conditions to prevent premature curing inside the bottle. Control plays a major role throughout the entire production cycle. Incoming raw materials are evaluated for purity, viscosity, consistency, moisture content, and particle stability. During manufacturing, technicians continuously monitor batch appearance, viscosity profiles, and dispersion quality. Finished coatings then undergo extensive performance testing. Hydrophobic behavior may be evaluated using water contact angle analysis. Hardness performance is commonly associated with ASTM pencil hardness evaluation methods. Additional testing may include abrasion resistance, chemical spot resistance, UV weathering, gloss retention, adhesion testing, and accelerated aging studies. Long-term storage stability also becomes critically important because ceramic coatings remain chemically active systems throughout their shelf life. Despite their premium appearance in consumer packaging, industrial ceramic coatings present several manufacturing challenges. Moisture sensitivity remains one of the largest technical obstacles. Even small environmental variations can affect viscosity stability, curing consistency, and long-term product reliability. Nanoparticle stabilization also requires highly optimized dispersion systems to prevent sedimentation or haze formation over time. At the same time, global VOC regulations continue pushing manufacturers toward lower emission solvent technologies while maintaining application performance and durability. Professional detailing businesses also demand coatings with smooth wipe-off behavior, predictable flash times, minimal streaking, and excellent gloss development. Balancing installer usability with high-performance chemistry remains one of the defining challenges of modern ceramic coating engineering. Ultimately, ceramic coating manufacturing represents a sophisticated combination of surface chemistry, nanoengineering, solvent science, and controlled industrial processing. From silane cross-linking systems to nano-silica reinforcement and moisture-controlled production environments, every stage directly influences the final coating performance experienced on the vehicle surface. As automotive protection technology continues evolving, manufacturers are investing heavily in more advanced hybrid coating architectures capable of delivering